Okay, thank you, and I'm glad that you're still here to hear about toric fiber products and geometric modeling. And this is joint work with Eliana and Ben Hollering. So let me start right away with our main result, and then as we go through the talk, I will explain all the ingredients, and hopefully in the end we will all appreciate the result. Okay, so the theorem says we have two polytopes. This is difficult from here. So we have two polytopes P and Q, and they satisfy a property called rational linear precision. So this is an important property from geometric modeling, which I will explain later. And what also belongs to this property are these weights. These belong to these polytopes. And then we say that we can construct another polytope by taking the toric fiber product, which will I explain later. And then this toric fiber product will satisfy the same very nice property of rational linear precision. And this property says something about the existence of so-called blending functions from geometric modeling. And we can explicitly construct these new blending functions. We can explicitly construct these new blending functions. And we give the description here. And what's very nice about this is that it connects geometric modeling, which is where these blending functions come from, and this property of rational linear precision. It connects this to the algebraic statistics, because the toric fiber product was usually, or previously, only known as a construction used in algebraic statistics, namely for exponential families, or as we already learned, toric varieties. And now we introduce the toric fiber product in the geometric modeling context. And in particular, we will see a nice kind of correspondence between toric patches and exponential families. Okay, so let me start by explaining what geometric modeling is. So briefly, geometric modeling is concerned with finding nice parameterizations of lines, surfaces, and maybe three-dimensional objects. And why do you want to have nice parameterizations? Because you want to represent your object in a computer. So maybe you're an architect and you want to design a roof of a building, and then you want to use some software in your computer to design this roof. So for example, maybe you know this Guggenheim Museum in Bilbao, and actually the roofs look quite nice, and they have been designed with precisely these tools from geometric modeling. So what is the context here? So we have a set of control points. These are just integer valued points, d-dimensional, and we have a set of blending functions. So basically for each point, we have one blending functions. And we also have positive real valued weights. And then they give rise to a patch. So this is our parameterization in the end. So we just sum over all these weighted blending functions multiplied by the points. And these points form a polytope by taking the convex hull. And then these blending functions are defined as functions from the polytope to the real numbers. And there's a normalization condition on these blending functions. And here you see a nice picture from Frank Stotile. So this is the patch you'll get in the end, and these blue points are some control points. Okay, and a very nice property that a polytope with some weights can satisfy is the property of rational linear precision. So this means that you can find blending functions that are particularly nice. So this means, so first of all, these are rational functions. So these are basically, it's a polynomial divided by another polynomial. They have to be somehow normalized. And they define a rational parameterization of some object that I will define later. They are defined on the interior of the polytope. And they satisfy this property of linear precision. And this can be rewritten that for any affine linear function, lambda, this satisfies affine invariance. So we can plug in a lambda here, and then we have to plug in lambda, apply lambda to all the points, and then these things are equal. So with this patch, we can replicate all affine linear functions. That's why this property of linear precision is really important and something we want to achieve. So the question is, what is this thing here, this xbw? And this is a scaled toric variety. So a toric variety in general is the Zariski closure of a monomial map. And in the case of scaled toric varieties, in addition to the monomials, we also have some weights or scalings. So this looks as follows. So this is a map from the complex algebraic d-dimensional torus to a projective space. And we take we have these given integral points, and we take the coordinates and exponentiate them to the power given by the coordinates of the points. We take the product, so this gives us a monomial, and then we multiply this monomial by some weight. So this gives us a parameterization. And then the Zariski closure of this is a variety, and this is the scaled toric variety. And this is a well-known object in algebraic statistics. And when we normalize correctly and we intersect with a positive orthant, then this will give us a discrete exponential family, what we have already seen in Eliana's preliminary talk. So this is a discrete exponential family, which I denote by M, and it lives in the open probability simplex. And what is nice about toric varieties in general is that much of the geometry of this toric variety can be actually translated into combinatorial properties of the polytope, which is the convex hull of all of these points that are in the exponents here. So for example, the degree can be read off from the polytope, or the dimension of the variety is equal to the dimension of the polytope, and so on. So the polytope gives us a lot of information about the variety. Okay, so here's some very short excursion to maximum likelihood estimation. So what is maximum likelihood estimation? So we have given some data. So in this case, this is some integer vector u, and we have a statistical model M. And now we want to find a point in the model that best explains the data. And to do this, we want to maximize this likelihood function here. And we want to maximize this function over the model. And how do we do this? Well, for example, we can do standard Lagrange multipliers. And for this, we are interested in the critical points of this likelihood function. And therefore, a nice thing that we study in algebraic statistics is the so-called maximum likelihood degree of this variety belonging to the model M. So the maximum likelihood degree is the number of complex critical points of this likelihood function. Well, and then we have to take the regular locus and exclude some hyperplane arrangement here. But I mean, more or less, it's just a number of complex critical points of this function for generic data. So it turns out that for generic data, this number is always the same. And now, how does this translate to geometric modeling? What does this have to do with the talk? So there's this nice theorem from 2010, which says that a polytope together with some weights has this very nice property of rational linear precision if and only if the corresponding toric variety has maximum likelihood degree 1. So maximum likelihood degree 1 is exactly this case Eliana talked about earlier, where the MLE admits a rational closed form expression. Okay? So now let me talk about toric fiber products. So here in this case, we want to take two polytopes, and they are given by 2 point configurations B and C. And this might look a bit scary, but it's really not. So these points in B, they have upper and lower indices. So upper indices are I and J. And points in C have the same upper indices as the points in B, but different lower indices. And they are equipped with a grading, or a multi-grading, by another set of integer points, which is called A. And they have the same upper indices, and only the upper indices. And this means we have a degree map, which is a linear map so we can grade all the points in B by saying the degree of Bij is this vector AI. And similarly, the degree of Cik is also AI. Right? So kind of the upper index of the points gives us the grading. And then this can be extended linearly. Okay, and the toric fiber product is we stack together all the points with the same grading. Okay, so we take Bij and Cik. So here we only have the points that have the same grading Ai, and we do this for all the correct indices. Okay, and then this gives us another polytope by forming the convex hull of this point configuration. And then this gives us, again, a toric variety. And this is this xb b times ac. And the question is, what happens to the weights? Well, and to the weights, well, it's basically what you might expect. We just have to multiply the correct weights with each other. So again, the weights. So we have a weight for each lattice point, and we have to multiply the correct ones. So every time we pair 2 points here, we also have to multiply the weights. So let's look at an example. So here we have the square, also known as P1 times P1. So we have these 4 lattice points, 0, 0, 1, 0, 0, 1, 1, 1. And we choose a grading such that 0, 0 and 1, 0 are graded by A1. So A1 in this case, so we have just A consists of A1 and A2, and we can think of this as the 2 standard basis vectors of R2. So 0, 0 and 1, 0 are both graded by E1, and 0, 1 and 1, 1 are both graded by A2. So these are the red and the blue points. And then we have the trapezoid. So to the algebraic geometry, this is also known as a Hirzebruch surface. And here we have the grading that 0, 0, 1, 0, and 2, 0 are graded by A1, and 1, 1, and 0, 1 are graded by 2. And now we have to choose the correct points and stack them on top of each other. So for example, we take B11 and C11, B11, C12, B11, C13, and so on. And then we have B21, C21, and so on. So this gives us a polytope in 4 dimensions. But this polytope is actually not full dimensional, but the dimension of this polytope is 3 dimension. And here we see a projection of this polytope. So this is the toric fiber product polytope with respect to this multigrading. Okay? And then there's a nice theorem that tells us how the ML degree behaves under toric fiber products. So this is a theorem by Carlos and co-authors, and it says that assuming that A is linearly independent, so for example, we take A to consist of standard basis vectors, then the ML degree of this toric fiber product variety is the product of the ML degrees of the toric varieties associated to the polytopes. Okay? So what do we know now? So we are starting with polytopes P and Q that have rational linear precision. And we have seen this theorem that rational linear precision translates into the corresponding varieties have ML degree 1. This tells us that the toric fiber product variety also has ML degree 1, which means that the toric fiber product polytope also has rational linear precision with the correct choice of weights. So this kind of statement is more or less immediate once we know about the other theorems. What's not immediate is the explicit construction of the blending functions. So we are given blending functions Bij and Bik, beta ij, beta ik, corresponding to P and Q, such that P and Q have rational linear precision with these blending functions. And now the question is, what are the blending functions for the toric fiber product polytope? And we can explicitly write this down, and we have not found one expression, but we have found 2 expressions here. And that's kind of funny because these 2 expressions are not the same. If you look closely, the denominators are different. So here we sum over all points in B with the correct grading, and here we sum over all points in C with the correct grading. And here's an example that this really matters. If we consider the square, then the square has rational linear precision if we take all the weights to be 1, And we have these set of blending functions. So these blending functions are actually quite nice. And they are called toric blending functions because you can actually calculate them from lattice distance functions in this case. This is because the square has an even stronger property called strict linear precision. That's why these blending functions look so nice. And the blending functions of the trapezoid are not as nice, but you can still compute them. And they are these rational functions here. And now this toric fiber product polytope has these weights. So this is just by multiplying the correct things with each other. And then one blending function here. So I call this beta 1, 2, 3. So this means we have to take, so remember that these 2 points were graded with 1, and these 3 points were graded with 1. So we take the second blending function here and the third blending function here. We want to combine them. Then the first expression in the theorem yields this expression here, and the second expression yields this term here. So now you see they are almost the same, but they're not exactly the same. So here we have an x2, and here we have a y2. But now if you look back to this example, then you see that, so here this row represents the x2 coordinate, and this represents the y2 coordinate. So you see that these two numbers are always the same. This means that these two blending functions actually agree as functions if you restrict them on the product polytope. Yeah, and that's actually the funny part about this whole story, that these two expressions here for the blending function are the same, and there's what I think is a very nice and geometric proof of this. And if you want to hear about this, you can read it in our paper. And with this, I'd like to thank you for your attention.
Thank you very much. Are there any questions?
So the blending functions mean what statistically?
Well, statistically, they are kind of related to the maximum likelihood estimation. So if you know the blending functions, you can compute a parameterization of the MLE. So it is a little bit involved, but you can do this pretty straightforwardly. Yes. So in some sense, they are a little bit stronger than a parameterization for the MLE. They contain a bit more information.
Any other questions? Okay, then thank you, Max, again, and thank you everyone for being in the session.